Hey everyone, so I just wanted to do a quick review of the first and second fundamental theorems of calculus. So let's go over the first theorem. The first theorem says that if you have some function g of x, it's going to look kind of weird. It's going to be equal to the integral from a to x of f of t dt. Okay? So let me quickly explain what I mean here. So first of all, I have this variable t that's being integrated over a function f, and I'm taking it with a definite integral with the bounds from a to x. And then I'm setting this to a function g of x. So first of all, x is a variable. A is a constant. Okay, that's important. A is a constant. So let me give you an idea of what I mean by this. So imagine we have some function, we're going to call it f. So this is f of t. And we're taking the definite integral, which we know to be the area under the curve, from a to some point x. And we're looking for this area. That's what the definite integral is giving us. Now this x, since it's a variable, is varying either way, right? Now there's confusion when it comes to the first fundamental theorem as to why we have two variables up here. We have an x and a t. Let me try to explain that to you. So it's kind of because they serve two different purposes. For one, we have this varying line right here that we're calling x, that's going back and forth. It can change, and that's our area, right? But to actually calculate the area, we need a definite integral, which is completely different than x, right? So to do this, we actually need a whole integral on its own that we're calling f of t dt. Because x is varying left to right, whereas t is varying on this curve to calculate the integral, like we talked about Riemann sums. That's what t is actually doing in this definite integral. It has nothing to do with x. So the reason why we need two variables is because they serve different purposes. X is a line changing for our bounds, whereas t helps us calculate the area. Calculate the area. So you see, we have two things that are varying and doing two completely different things. If we had x included in this integral, it wouldn't really make much sense, right? Because then there wasn't too much meaning to this line going back and forth. It wouldn't make any sense if we had it in the integral and also changing this line at the same time, right? So that's why we have two variables. And the reason why this g of x is helpful is because we can actually say the derivative of g, or g prime of x, is actually just equal to our inside function applied at x. So to release any confusion, in the integral we have it in terms of t, which we call a dummy variable. Whereas here, the derivative is in terms of x. The reason why this happens, we'll go over once we talk about the second fundamental theorem. It'll be much more clear. But just for some intuition, right? This g is in terms of x. So when we're taking the derivative, we're going to get another function in terms of x, right? So what kind of happens is when we take the derivative, this x that was the upper bound goes inside the function, right? So that's basically what's happening here in the second fundamental, or the first fundamental theorem. So let me give you a quick example. So let's find the derivative d dx from the integral from 2 to x of 1 over t squared plus 1 dt, right? And before I show you the solution, I want you to pause the video until you completely understand why I wrote d dx instead of d dt, okay? Because that's an important conceptual understanding here. So, using the first fundamental theorem, we know that g prime is actually just equal to f applied to x, which is going to be 1 over x squared plus 1. This is just as simple as replacing t with x here. Now, the examples will get a little bit more complicated once we go over the second fundamental theorem. So the second fundamental theorem is honestly the better one in my opinion. It's very, very helpful when it comes to solving definite integrals. So if we had the definite integral from a to b of f of t dt. So basically, if we have a picture, we're taking from a to b and we're finding this area, right? That's what this integral is doing. Then this is simply the antiderivative or integral applied at b minus the integral applied at a. And remember, we usually use this capital F to denote the antiderivative or integral of f. So this is really helpful, right? Also, if you're wondering, sometimes this is written as f from b to a, or something like f of x, or sorry, f of t, like that, with a stick or a line. So the reason why this is helpful is because it's, honestly amazing for solving definite integrals, right? We know how to do regular integrals, and now there's this amazing connection between the two that's not completely obvious. So let's do one example before I show you how this links to the first fundamental theorem. So let's say we had the integral from 0 to 2 of x squared. Well, this is simply 1/3 x cubed applied from 0 to 2. If we plug in 2, we get 8 over 3. Subtract at 0, which is just going to be 0, we get 8 over 3. An exact answer that was pretty easy to find to a complex problem, right? So this second fundamental theorem is going to be key to understanding how to solve definite integrals. And there's a lot of other tricks that we won't go over just now. But you should definitely commit this to memory. Hopefully throughout the course we'll be proving more of the theorems, but this one is one you should definitely commit to memory. So I want to give you an important example. If we take the integral from a to x of f of t dt, using the second fundamental theorem, well, this is just f of x minus f of a. Right? That's exactly what the second fundamental theorem says. It says, take the top thing, subtract the bottom thing. So that's what I did. Now, what happens when I take the derivative of both sides? Right? Well, f of a is just a constant, so this is just some number. The derivative of some number is 0. So this goes to 0. What's the derivative of the antiderivative or the integral? Well, it's just the function, right? You just get f of x. So what we've proven is g prime of x equals f of x, which is exactly what we said in the first fundamental theorem. So hopefully, if that's a little bit confusing for you, but you understand this theorem, they connect in this very obvious way, right? And I want to show you an even more conceptual understanding of the first fundamental theorem. What if we took the integral from a to some function u of x? So u, if we imagine our example again, we have a and we have x, and u is telling x to go here, here. It's some function of x that's dictating where it goes, right? This is a little bit more complicated than just a regular variable. X of f of t dt. Well, this is going to be equal to f, capital F, of u of x minus capital F of a. When we take the derivative, once again, this goes to 0. And now we get this kind of mess of a function. Luckily, we have the chain rule. which we know what to do. This is when you have two functions, f of g of x, and you want to take the derivative, which is just equal to f prime of g times g prime. So all we get is f of u of x times u prime of x. Okay, so let's see that in action. What if I had the integral of d dx 3 to x cubed of, let's say, square root of t squared plus 1 dt. So x cubed is kind of equal to our u here, right? So we know that this is actually just going to be equal to f of u. So we get square root of u squared plus 1 times u prime, which is just 3x squared. In other words, the derivative of x cubed. And then, to simplify, we plug in x cubed for u, and we get x to the 6th plus 1 times 3x squared. Just that easy. So, to make matters simple, basically all you're doing is when you have, technically you're doing the same thing when you just have x, but always you plug in your variable into the thing inside of the integral and you multiply by its derivative. So if you had x, the derivative of x is just 1, right? So it works out nicely. But if you have x cubed, you plug it in the same way you would do with x, and then you multiply by 3x squared. That's all you do. So hopefully this kind of cleared things up when it came to the first and second fundamental theorem of calculus, and thanks for watching.